So far we have discussed differential equations which depends on only one independent variable. In all the four differential equations that we have discussed, Legendre, Hermite, Logger and Bessel, there is a single independent variable x and the y depends on x only. But in physical problem, when we want to describe a different dynamical system, a dynamical system is one whose property changes from point to point and with time also. And so if we want to describe a dynamical system, then single independent variable do not serve our purpose. As for example, if we want to describe a plane progressive wave y is a function of x and t, and we can write it as e to the power I kx minus omega t. This is the plane progressive wave. If we want to know what is the amplitude of the wave at a particular instant, say we have a reference point which is x0 t0, and if we want to displace x such that x is equal to x plus dx, what will be the fate of the wave function? This is given by a Taylor expansion of y about x0. So we get y at xt is equal to y at x0 dx t0. Sorry, this is t0. So this is basically y at x0 t0 plus del y del x at x0, if we keep only up to the first order term. And if we change time t to t0 plus dt, then the situation y at x0 t is given by y at x0 t0 plus del y del t at t0 plus higher order terms. And if we change both x and t, then the partial derivative with respect to x as well as with respect to t will come into play. And such dynamical system is better described by differential equation involving partial derivative with respect to more than one independent variable. As for example, here the two independent variables are position x and time t. Such differential equation is known as partial differential equation. As for example, this equation is related to del x2 is equal to 1 by v square del 2y del t2, where v is the velocity of wave propagation. This is omega by k, with v is equal to omega by k. So we define partial differential equation as a differential equation which involves the partial derivative of a function. In contrast to partial differential equation, we have ordinary differential equation, where the function to be found out depends only on one independent variable. In that sense, Legendre, Hermite, Logger, Bessel, these are the examples of ordinary differential equation. So this is a wave equation which is a partial differential equation involving two variables x and t. If we consider two independent variables to be x and t, then the most general form of a second order partial differential equation in two variables is second order partial differential equation in two variables. The variables are x and y is of the form a del 2u del x2 plus twice b del 2u del x del y plus c del 2u del y2 plus d of del u del x plus e del u del y plus fu is equal to 0 if it is by homogeneous. Where a, b, c, d, e, f, they are functions of x and y. A, b, they are functions of x and y in general. Now, if we compare this equation with the second order algebraic equation is ax square plus twice bxy plus cy square plus dx plus ey plus f is equal to 0. We know that these are depending on the relative values of a, b and c. That is, if we define delta is equal to ac minus b square, then depending on the value of delta, we can have different curves. So when delta is equal to 0, we have parabola. When delta is less than 0, we have ellipse, and when delta is we have hyperbola. Keeping a similarity with this nomenclature, we define a quantity delta is equal to AC minus B square. And when AC minus B, this is 0, we say the differential equation to be parabolic. When this is less than 0, we say it elliptic, and when greater than 0, we call it hyperbolic. So this is the classification of second order partial differential equation. Note one thing, that this equation, it is a second order partial differential equation, but still it is linear because there is no product term involving u and its derivatives, partial derivatives. So this is a linear equation. Now we shall consider a few simple, few very common equation, differential equation, a partial differential equation appearing in physics. First equation is the Laplace equation. Common partial differential equations in physics. One is Laplace equation. This is the Laplacian. This equation arises in electrostatics, and this describes the electrostatic potential at a point not occupied by charge. Poisson's equation, if the point under consideration is occupied by a charge, then it is given by Poisson equation, where rho is the charge density. Then wave equation. The wave equation is this describes the elastic wave. as well as the electromagnetic wave equation. Each component of electromagnetic wave satisfies this condition. If we separate out the time part of an wave equation, then we get Helmholtz equation. This is Helmholtz equation. This is the special part of an wave equation. Then we have heat conduction equation or diffusion equation. Diffusion equation. This is the diffusion equation involves second derivative with respect to space coordinate and first derivative with respect to time coordinate. Then we have time independent Schrödinger equation. Time independent Schrödinger equation. This describes the stationary states of quantum system, which is minus h line square by twice m phi of r, where E is the energy of the system. And then time independent Schrödinger equation, this is time independent, and then time dependent Schrödinger equation. This is these are the few common partial differential equations of physics. Amongst these, in our curriculum, we have to solve this equation, and this equation. And these two will be used very frequently in quantum mechanics class. And since this equation can be converted into it will be also in our consideration. Among now we want to see the nature of the equation. This definition of partial differential equation holds only for function or partial differential equation involving two variables. So we will restrict ourselves to two variables only, as for example the variables will be x and y over here, here we have considered x and t, this is x and y, this is again x and t, and these two here we can consider it x and y, and this is x and t. Because the classification of partial differential equation that we have presented here is applicable for two variables only, and these two equations this is just a inhomogeneous differential equation, and the corresponding homogeneous part is the Laplace equation. Now this equation in two dimensions becomes del 2 psi del x2 plus del 2 psi del y2 is equal to 0. So we have A is equal to B is equal to 1 and C is equal to 0. So delta that we have defined, delta, we define delta is equal to AC minus B square. And AC this is greater than 0, so the equation is elliptic. So this is elliptic equation. This is the Laplace equation. Then coming to wave equation. Wave equation in 1D becomes del 2u del x2 minus 1 by v square del 2u del t2. Here t is actually to be treated as y is equal to 0. So we have a is equal to 1, b is equal to minus 1, c is equal to 0. So this is hyperbolic. The wave equation is hyperbolic. Now coming to diffusion equation. This is del 2u del x2 minus 1 upon sigma square del u del t. So we have a is equal to 1, b is equal to c is equal to 0. So delta is 0. So it is parabolic. This differential equation is parabolic, and other things can be treated similarly. So we have considered we have stated the classification of partial differential equation involving two variables, and cited 3 examples for each one of these three: elliptic, parabolic, and hyperbolic. What happens when there are more than 3 independent variables are involved? Obviously, this classification, the definition of classification of partial differential equation no longer holds when there are more than 2 independent variables involved, and in all of the cases there may be more than 3 variables. As for example, in electrostatic problem in 3 dimension, the independent variables would be x, y, z, or r, theta, phi, and so on. So there may be 3 variables. There may involve 4 variables. This equation may also involve 4 variables. This may involve 3 variables, and this may involve 4 variables. So we are to generalize the definition for the nature of partial differential equation. We will go for this generalization, and to recall that we use Laplace equation as parabolic. Elliptic, then this equation is hyperbolic, wave equation is hyperbolic, and we consider the diffusion equation to be parabolic. That is what we have done. Now we are going to define the nature of the partial differential equation, second order partial differential equation involving more than 2 variables. Second order PDE in more than 2 variables. We consider the variable to be x1, x2, right up to xn. So the differential equation may be, if we take the example 3, n is equal to 3, then it may be del 2u del xy del 2u del x, the second derivatives of this. Then the cross derivatives there may be such terms, del x1, del x3, del x, etc., and there may be term del u, del x1, del u, del x2, etc. So we may write this as summation over ij is equal to 1 to n ai aj del to u del xi del xj plus the first derivative. This involves the second derivative term such that this is 1 1, this is 2 2, this term is 1 2, I is equal to 1, j is equal to 2, etc. Then we have I is equal to 1 to n bi del u del xi plus cu plus d is equal to 0. If the equation happens to be homogeneous one, as we have considered here, then d is 0, and otherwise d is non-zero. So this term considers the 1 1 term, 1 2 2 3 3, 1 2 1 3. So the combination is 1 1 1 2 1 3 2 2 2 3 and 3 3. These are the terms included here. Over here, sorry, this is 2 1 2 2 2 2 3 3 1 3 2 3 3. But these terms are in general equal because in most of the cases it is found that the partial derivatives are independent of the orders, and so is this. They are found to be same. So to say, if we define a matrix, square matrix A, as the matrix comprising of the elements A, I, J, it is a real square symmetric matrix. So we can find out its eigenvalues and eigenvectors. So this matrix is a matrix of order n. When then it will have eigenvalues, A matrix will have m eigenvalues. Coming to partial differential Laplace's equation. Laplace's equation is in this notation. This is del 2 phi del x12 del 2 phi del x22 del 2 phi del x32 is equal to 0. So we have the costa, the matrix A will have only 1 1, the matrix A will have only 1 1 term, 1 1 2 0. There is because there is no mixed derivative involved in this equation. So this equation is diagonal, and these are the eigenvalues of it. So we see that all the eigenvalues are positive. When all the eigenvalues are positive, the differential equation is called to be elliptic. This is the definition of elliptic differential equation. Now we come to the wave equation. For the wave equation, we have the wave equation is del to u minus 1 by v square del to u del t2 is equal to 0. So if we write it this is del 2u del x1 2 plus del 2u del x2 2 plus del 2u del x3 2 minus 1 upon v square del 2u del x4 2 is equal to 0, where x1 is x, x2 is y, x3 is z, and x4 is t. And the corresponding matrix A will be a matrix of dimension 4 by 4 matrix. Here again, these are the diagonal elements are the eigenvalues, and we see that all the eigenvalues are positive except one. Such a case, it is called parabolic. So parabolic differential equation, hyperbolic differential equation. Hyperbolic differential equation has the signature that all the eigenvalues are non-zero and one has opposite sign. Only one is negative and all others are positive. So we differentiate between elliptic and parabolic. Hyperbolic partial differential is as one for both elliptic and hyperbolic partial differential equation. The eigenvalues of the coefficient matrix A, all the eigenvalues are non-zero, and for elliptic one, all the eigenvalues are positive. For hyperbolic partial differential equation, only one eigenvalue is negative and all others are positive. Now coming to the diffusion equation. The diffusion equation is so in 3 dimension this reads like del x3 2, and this part is 0 times del 2u del x4 2, and we have minus 1 by sigma square del u del x4 is equal to 0. So the matrix, A matrix will be 1 0 0 0 1 0 0 0 0 1 0 0 0 0 0. One eigenvalue is 0. So this is the definition of parabolic partial differential equation. We see that the two definitions, first definition were applicable to partial differential equation involving two variables, and the latter definition of the classification of partial differential equation is applicable to second order differential equation of any number of variables. With this short introduction, we shall now come to the how to solve partial differential equation. The partial differential, so to say, that there is no standard technique for solving partial differential equation. It is found that in most of the cases, in few cases, that the partial differential equation under consideration can be solved very easily, and in some other cases the solution is very difficult. Few special techniques is available, as for example the wave equation. If we consider a wave equation in one dimension, then this equation is del 2u del x2 minus 1 by v square del 2u del t2 is equal to 0. This differential equation can very easily be solved if we use redefine two variables u xi and eta, then this differential equation can have very simple solution. It is found f of xi plus f of eta form or g of eta form, and well both f and g obeys the harmonic nature. That means but this is a special, very special case applicable to wave equation. This is known as Helmholtz solution. In general, it is very difficult to get the solution analytically, and one has to take help of numerical methods. But there is a very useful technique called separation of variable technique, which is our primary concern in this curriculum. That is, our aim is to solve up the partial differential equation under separation of variable technique. Let me first explain what is the method is. Solution of partial differential equation, separation of variable technique. Let us start consider a partial differential equation, that is del 2u del x2 minus 1 by v squared del 2u del t2. This is a wave equation in 1D. This is wave equation in 1D. Now we know that u is a function of x and t. In separation of variable technique, we assume that it can be written as a product of x and a product of time function. So we assume that the solution can be written as the product of a function of one variable x and another variable t. So where x is a function of x only, and where t is a function of t only. So we assume that the solution can be written in the product form. If this is not the case, then the separation of variable technique fails. So this technique is very helpful only when the solution can be written as some function depending on variable 1, then multiplied by a function which depends on variable 2 times a function which depends on variable 3, and so on and so forth. If we differentiate this one with respect to x partially, so what we will have, del u del x is basically so this is derivative of capital X with respect to x times t. So we have this part is 0 because t doesn't have any x dependence as per our assumption, and since capital X depends only on x, we have used total derivatives instead of partial derivatives. So del has been replaced by d. So the result is t times dx d of x. We can write it as t times x prime. There is no confusion using this, because when we write capital X, it is in our mind that capital X is a function of small x. So the prime means it is the derivative of capital X. So the non-trivial derivative is the derivative of capital X with respect to small x. In this way we get del 2u del x2 is equal to t times x double prime. Similarly, del u del t will lead to del t of x of x times t of t. This is del x del t times t plus x times dt, d of small t. This is 0 as capital X doesn't have any t dependence and capital T has sole dependence on small t, so we have used total derivative instead of partial derivative. So this is x times dt dt, which can be written as xt dot. Here we have used the convention dot to represent partial derivatives with respect to time and prime to represent derivative with respect to space coordinates. So in this fashion we get del 2u del t2 is equal to x t double dot. If one uses prime for both x and t, in that case even no confusion will arise, because if we write x double dot, that means x is a function of small x only and its second derivative, then it is obvious that this represents del 2x del x2. Similarly, if we write t double dot, this means, so no confusion will arise, at least in this case, in separation of variable technique, if we use prime or dots to represent partial derivatives or derivatives. However, we shall use prime to denote partial derivative with respect to space variables and dot to represent derivative with respect to time variable. So the left hand side with this, the if we use this equation and use this answer, this left hand side, because this part becomes t times x double prime, and we take it on the other side, this is 1 by v square, this part is capital X times t double dot. Or the solution of the equation is u of xt. Recall that it is x of x times t of t. A solution could be obtained in the form which is 0 always, then left hand side is 0 and right hand side is 0. So this is a solution, but this solution for all x and t, this is known as trivial solution. This does not reveal any dynamics of the system and is not of interest to physics. Although it is a mathematically acceptable solution, but it is not of any interest to physicists, and we want to consider only those solution which is not identically 0, that is called non-trivial solution. The solution may be 0 for a specific value of x and t, but not 0 identically. So we write for non-trivial solution, we divide both the sides by x and t to get x double prime by x is equal to 1 by v square t double dot by t. So this is the transformation from here to here there is all possible only for non-trivial solution. For trivial solution, the division by 0 is not defined, so we cannot land up to this equation. Remember this is a very important point, that is, this form of the solution is obtained only when we seek for a non-trivial solution. Now you see the left hand side has kept only x dependence, and right hand side is independent of x. It is in particular case it depends on t only. Left hand side depends only on x and right hand side is independent of x. Still the left hand side and right hand side is equal for all values of the independent variables. This is possible only when, if and only if each side is separately equal to some constant. So the left hand side has only x dependence and the right hand side is independent of x, and they are valid for all values of x and t. This is possible only when each side is separately equal to some constant called separation constant. Separation constant. The nature of the separation constant is very important. Let us choose that this separation constant to be minus alpha square, where alpha we choose to be a real quantity, where alpha is real, alpha is a real quantity. If alpha is real, then alpha square is positive and overall separation constant has been taken to be negative. If we choose this, then we have x double dot minus alpha square x is equal to this, which leads to x double prime plus alpha square x is equal to 0. Since alpha square is real, it has harmonic solution, sinusoidal solution. It has sinusoidal solution. That is, x can be written in terms of a cos alpha x plus b sin alpha x, or it could be written a e to the power I alpha x plus b e to the power minus I alpha x. One thing is very clear, that the name alpha would have been much better if we use, instead of alpha, k square. Then we can identify k as the wave vector. This is the sinusoidal solution in terms of stationary waves, and this is the sinusoidal solution in terms of progressive wave. So this is the stationary wave solution, and this is the progressive wave solution. Progressive wave solution. When there is a tendency that a wave traveling in a medium gets reflected from the boundary, then it is found that the stationary wave solution gives you is very much helpful. And on the other hand, when a wave traveling in a medium enters into the second medium, then this progressive wave solution becomes very important. You see that if one chooses the separation constant to be plus alpha square, the solution would be x double prime minus alpha square x, which is an exponential function. But we know that we are trying to get a solution of an wave equation which has periodicity in space as well as time. So we choose our separation constant in such a fashion that the periodicity is retained. Now the time equation is very obvious. So from this we get the time equation to be 1 by v square t double prime by t is equal to minus k square. We used alpha square, and for this we write minus k square, or we get t double dot plus vk whole square t is equal to 0. This is omega. So the solution is t double dot plus omega square t is equal to 0, which has a solution t of t is equal to e to the power plus minus I omega t. So we see that the separation of variable technique returns back the progressive wave solution for this differential equation. So what we have done in separation of variable technique, we first write the trial solution as the product of functions, where each of the function on the right hand side depends only on one independent variable. So if we have the 4 independent variables x, y, z and t, then it should be written capital X of x, capital Y of y, capital Z of z, and capital T of t. Then we apply this answer into the differential equation, and we remember that each of the function on the right hand side has dependence only on one of the variables, and we get such an equation. Now for non-trivial solution, we divide whole thing by this answer, the solution, and we get such an equation. We instead take one function on the left and take other on the right. As for example, if we consider the variables to be x, y, z and t, then we say we take the x part on the left and y, z and t part on the right, and we argue that the left hand side depends only on x while the right hand side is independent of x. So this side, both the side must be separately equal to some constant called the separation constant. The separation constant is so chosen that the physical nature of the problem under consideration is retained. As for example, if we know that the function, the solution should have periodicity with respect to x, then we should choose the separation constant to be minus of some real number, to retain the minus of some real number, so that the resultant equation has sinusoidal behavior. In the next step, say we take we equate this with the separation constant. So in this case it has y, z and t dependence. Then we take y on the left, and right hand side left hand side will have the dependence on y, and right hand side will have the dependence on z and t, and we argue the left hand side is y dependent and right hand side is independent of y, so we introduce another separation constant. And in the third step we decouple z and t. So if we have more than 2 variables, then this equation can be decoupled in n-1 steps by introducing n-1 separation constants. And ultimately what we get in a partial differential equation involving n variables is ultimately reduced to, in separation of variable techniques, into n ordinary differential equations. And the separation constant, it is the main crucial, the choice of the separation constant is very crucial because it determines the physical nature of the system. So this we end our discussion today. We shall consider a few examples in the next class to describe the partial differential solution of partial differential equation by using separation of variable techniques.